Simulation of Dadar Station Transit Hub. Dadar Station is the biggest interchanging point of the Mumbai Suburban Railway. It is the junction point of Western and Central railway lines. The objectives of our simulation model are to absorb the length of average waiting queues in each boarding direction, to study the convenience factor, that is the comfort level of passengers in switching the trains, to study the underuse and overuse of Mumbai local trains during peak hours. This is the original station map. To approximate the station into our simulation model, we have made the assumptions. We have merged the slow and fast trains traffic. Instead of using multiple lines, we make use of 4 lines: western up, western down, central up, and central down. We take north direction as up and south direction as down. This is the simplified description of the system we simulate. We show 8 types of railway line switches: central up to western up, central up to western down, western up to central up, western up to central down, and the others are shown in the bracket. The diagram on the right shows the switches that we try to simulate. For example, the central up to western down switch is represented by the purple dotted lines. The description of the system that we are simulating are as shown in the table. The components of the system include the system itself, that is the Dadar railway station, the entities of interest, that are the passengers, the features, that are the count and the arrival rates, the activity that they perform, that is switching off the railway lines, the resource they use, that is the trains, the state variables, which include train arrival rate and the number of passengers waiting, and finally the events, which is the arrival and departure of trains. We collect the input data for this simulation by using the Mumbai Railway Vikas Corporation Limited report given in the Indian Railways database. The following data was collected: the hourly arrival rates of passengers, the arrival rates of trains, and the capacity of trains.
From data we collected, we calculated arrival rates of passengers coming from different directions, and we marked them as the sources, like western up sources, western down sources, central up sources, so on. And this last entry is for the passengers coming directly at the Dadar station. Like the first entry shows that 1676, that is 1676 into 100 number of people per hour coming at Dadar station in the time interval 7 to 8. Similarly, 4534 into 100 shows the number of people coming from western up direction at Dadar station. And further, we figured out using the regression methods that how this western up source is getting splitted in the different boarding directions. For example, we have assumed that nobody is going back from the direction which they are coming. That's why the entries at the diagonals are 0. And here this 0.4 shows that the percentage of people, like we can say 40% of people which are coming from western up direction are switching trains towards the western down boarding direction, and 5% people are going in the central up boarding direction, 30% people are going the central down boarding directions, 25% are exiting the station, and so on. This is our simulation model, and this model is mainly divided into 4 parts if we look up closely. The first part contains the western up source and the western up boarding direction. So what is happening here, every source is divided into some boarding directions, and every boarding direction is collecting passengers from different directions. To have a closer look, we can see here that western up source is split in WCO. This implies that from western up, passengers are going towards central up direction. From western up, passengers going towards central down direction. From western up, passengers are going in the western down direction. This was western down direction. So here we introduced no delay because they are continuing in the same train. And this is the number of this is the fraction of passenger which is exiting the system. And if you look closely at the western up boarding, it is getting merged to different sources. running the simulation model for given input data, we collected the outputs for each hours. So let's say for morning 7 to 8 a.m. In the western of boarding direction, length of queue for per hour is 311 into 100. Each data is in the multiple of 100. The western downboarding direction, the number of people in queue for 1 hour is 220 into 100, and so on. And we can see here that the some cells are showing so many people. So these are the overcrowded peak hours. Further, we calculated cumulative queue lengths for per hour after combining all boarding queues. So in the like morning 7 to 8, we can say approximately 90,000 people are in the boarding queue. For 8 to 9, we can say approximately 240,000 people are in boarding queues, and so on. For 9 to 10, we can say approximately 270,000 people are in boarding queues. Now we calculated this data against the time and number of trains in that time interval, and on the y-axis we have kept number of boarding passengers. So we can see the one line is relatively lower, and that line is central of boarding, which is line going towards Thane or Kalyan, we can say. So in the morning, the number of people going towards Thane or Kalyan is very low compared to other direction. We introduced new entities here. So what is threshold? Threshold is defined as the train's carrying capacity. From given data, we have figured out like approximately 1200 seats are for seating passengers, and approximately we can accommodate 800 passengers in standing. So overall, the threshold for per train is 2000 people. Now we found overall threshold for an hour using the number of trains. Like in 8 to 9, the threshold is little higher because there are 21 trains. So 8 to 9, 9 to 10, 10 to 11, in every session there are number of trains are 21, and then threshold is decreased. So how this threshold is giving us some insights. So we can see those other lines are number of boarding passengers per hour. If a line is crossing a threshold, then we can say in that region the number of available seats are much lesser than number of required seats. So we can say there is surely a level of discomfort. But if the lines are well below this threshold, we can say the number of available seats are much higher than the capacity. If they are closing, and if they are intersecting somewhere, we can say okay, they are matching, our threshold is matching the required capacity. Now we try to measure level of discomfort at the basis of number of vacant seats, at the basis of seats which are not available. So what these cells shows, like if this data is showing minus 36, so we can say in the 8 to 9 a.m. approximately 3600 seats we are lacking in the western of boarding direction. We can say in the 9 to 10 approximately 12,500 seats we are lacking. Approximately here like 14,900 seats we are lacking the central down direction. So whenever there is a negative data, we can surely say those directions or people in those directions are suffering from overcrowding. We again calculated ratio of required seats versus available capacity in each direction and in different time segment. So like in 7 to 8, we assumed based on the number of trains available that per minute our capacity is 500, and the western up requirement was 189, so this ratio is like less than 1. So whenever a ratio is less than 1, then there is no problem. So this all things are is all ratio are less than 1, so these region lie in the comfort zone. But whenever this ratio is greater than 1, let's say here 1.07, 1.21 or 1.18, so we can clearly see here that number of available seats are lesser in compared to required seat. So we just try to make a baseline, the baseline one which is shows the, we can say, neutral experience. So if this capacity used ratio is greater than 1, we can say these bars lie in the discomfort zone. And if this ratio is less than 1, we can say here our train capacity is underused. What is our conclusion? We can first observe that between 8 a.m. to 11 a.m. Dadar station is highly inconvenient for exchanging the train services, because mostly discomfort zone lie in this region. And second thought is about second conclusion is about the threshold capacity. So we can increase a threshold capacity either by introducing more number of trains or by increasing per train capacity, and to optimize the capacity use. So this is very important, because in some cases train capacity is underused, and some cases train capacity is overused. So we can introduce some new services which are originating and terminating at the other station only at the specific times, mostly at the peak hours. Thank you. Thank you.